So today we are going to continue our discussions of bound state theory. And one of the questions we are really going to get at today and going to try to build up a real intuitive understanding is this issue of why it is that we get only certain discrete allowed energies in quantum mechanical systems. From a classical point of view, this is actually a little bit mysterious. You would think, for example, classically, that an electron orbiting around a nucleus could take on any energy value, but instead we get these discrete energies, but we only find them as discrete energies in the case of bound states, not in scattering theory, where we could actually have any value for the energy. So today we will really understand where that comes from. And all of this that we've been building up for this understanding is coming through this example that we're working through of the finite square well. Now, what I really find enjoyable about this particular example is a number of things, right? The first is that it does have real technological implications. We really do solve these types of problems, for example, when we are designing something known as a quantum well laser or other semiconductor quantum well devices. The other thing that's very nice about this example as we work through it is that it allows us to understand, it really exposes very general features that we would expect of bound states for any kind of a system, not just the finite square well. And we will be sure to emphasize to you the generality of some of our conclusions. And finally, of course, it is a particular solvable example. It's not a trivial example. So this really is a great way of teaching methods for solving for bound states in quantum mechanical systems. So let's then jump right on in. Let's first recall what we had figured out last time, and then take the discussion on from there. So last time, we were, just to remind you of the problem we're looking at, the finite square well has a certain potential V0 for values of x less than minus a and for values of x greater than plus a, regions which we call region 1 and region 2, respectively. Now, in the in-between region, between minus a and plus a, the potential then drops down to 0, and this then makes up the well or the dip in the potential. Now, the behaviors of the solution that we're looking for are these bound states. So their energy values that we're looking at, here's a sketch of a typical bound state energy, must be less than the energy as we go out towards positive infinity and also towards negative infinity. So it must be less than the minimum of whichever asymptote is the lowest, V as towards plus infinity or V towards minus infinity. And when we are looking at energies in this range, then we have these three different types of regions. Well, really, region 1 and region 3 act in very much the same way. They are both classically forbidden region, where we have curvature always away from the axis, characterized by a curvature constant given to you here by the usual formula that we've seen several times in the past. In region 2, though, we then have a classically allowed region, which is described by sinusoidal functions, which are always curved towards the axis, with that curvature characterized by this expression for the wave vector k, which is a usual expression that we've seen in the past. And finally, later on in the lecture, it will be useful to actually relate alpha and k because they are not completely independent. They are connected together through a relationship with a constant that characterizes the strength of the potential. In particular, if you take k squared and add to it alpha squared, you can see algebraically the energy terms will cancel and you're left just then with 2m v0 on h bar squared. So the hypotenuse of this triangle, which we will call q0, we can define then as this root 2m over h bar squared times the potential v0, and this then is just a constant then which characterizes for us the strength of our potential. Now, in addition to being aware of these formulas, there's one general trend that I'd like to point out because we're going to be building upon it in just a moment. And that is, in fact, what happens as we vary the energy to these various curvatures. So notice that this curvature constant alpha, its strength depends upon the difference between V0 and the energy E. So as I increase my energy upwards, this curvature in these forbidden regions will actually be decreasing. So I just want to put in little parentheses here to remember that if the energy starts going up, this alpha value, in fact, would start going down, as with this alpha value being the same value. So we will expect less curvature in the forbidden regions as I increase the energy. On the other hand, as I increase the energy, this K, which depends really just on the value of the energy, is represented by this difference here. K actually will be increasing as I increase my energy. Now, in terms of these curvature constants, the final thing that we need to remind ourselves of is the form of the solution we found to the time-independent Schrodinger equation. All of the terms that we solved for in the previous lecture all carried a certain prefactor on them. They all had a common factor of D1, so I've taken the liberty to factor that out of all of my solutions, because after all, at the end of the day, it will just represent some kind of a normalization constant. The way we solve for this, you will recall, is that we were solving our equations from left to right, satisfying the boundary conditions in that order. We have a boundary condition that as we go out towards negative infinity, it's a classically forbidden region, we need an exponentially decaying solution. So I'll sketch for you here what that might look like, right? So if I'm going to be decaying exponentially off as I go in that direction, so this is a sketch of phi of x, that means I'm only allowed to have a growing exponential solution. So this exponential form then is how we build in that boundary condition at infinity. We also anticipated the boundary conditions that would take place at x equals minus a, so we appropriately centered this function at x minus, at the location minus a, thereby writing it as a function of x plus a. Next, we then attached this forbidden region solution, phi 1, to the solution in region 2, which then was a sinusoidal type solution. And we had actually solved for the prefactors on these sinusoids so that we would match the slope and value of my wave function continuously as we then begin to enter into region 2, which would then have some kind of downward curvature controlled by the curvature constant k. Notice also that I wrote these as centered at the location x equals minus a in order at x equals minus a in order to precisely be able to match conveniently these boundary conditions. Finally, we anticipated that in region 3 we would have exponential solutions, which we chose to write as hyperbolic cosine and hyperbolic sine, centered appropriately at the boundary x equals plus a as the most convenient form to make the algebra simple, to pick off the corresponding prefactors, which I've solved for you here. And those prefactors were chosen specifically to again match the value and slope of my wave function as I enter into this final forbidden region in which the wave function has to always curve away from the axis, and so there will be some kind of curvature behavior like so. And our next task then is to finally understand what happens to the final boundary condition on the far right as we go out towards positive infinity. And that's where we will begin to take up our discussion.